Lesson: Model Evaluation and Validation. Model evaluation and validation are critical components in the application of machine learning to cybersecurity. The efficacy of a machine learning model in identifying, predicting, and mitigating cyber threats hinges upon the rigorous evaluation and validation processes it undergoes. These processes ensure that models are not only accurate, but also generalize well to unseen data, ultimately enhancing the robustness and reliability of cybersecurity systems. The first step in model evaluation involves splitting the available dataset into training and testing subsets. The training set is used to train the model, while the testing set assesses its performance. This split is vital to avoid overfitting, where the model performs exceptionally well on the training data, but poorly on new, unseen data. Overfitting is a significant concern in cybersecurity because an overfitted model may fail to recognize novel attack patterns, leaving systems vulnerable to new threats. A common practice is to use a 70-30 or 80-20 split for training and testing datasets, respectively. To further ensure the model's validity, cross-validation techniques such as k-fold cross-validation are employed. In k-fold cross-validation, the dataset is divided into k subsets or folds. The model is trained on k1 folds and tested on the remaining fold. This process is repeated k times, with each fold serving as the testing set once. The performance metrics are then averaged to provide a more robust estimate of the model's performance. This method helps in mitigating the variance associated with a single train test split and provides a more comprehensive evaluation. Evaluation metrics are essential in quantifying the performance of a model. In the context of cybersecurity, metrics such as accuracy, precision, recall, and F1 score are frequently used. Accuracy is the ratio of correctly predicted instances to the total instances. However, accuracy alone might not be a sufficient metric, especially in cases of imbalanced datasets where one class significantly outnumbers the other. For instance, in intrusion detection systems, the number of normal activities far exceeds the number of intrusion attempts. Thus, a model that predicts all instances as normal activities might still achieve high accuracy, but would be ineffective in detecting intrusions. Precision and recall provide deeper insights into the model's performance on imbalanced datasets. Precision is the ratio of true positive predictions to the total positive predictions made by the model, reflecting the accuracy of the positive class predictions. Recall, on the other hand, is the ratio of true positive predictions to the total actual positives, indicating the model's ability to identify all positive instances. The F1 score, the harmonic mean of precision and recall, balances the trade-off between precision and recall, offering a single metric that accounts for both false positives and false negatives. In cybersecurity, a high F1 score is crucial, as it ensures that the model effectively identifies threats without generating excessive false alarms, which can lead to alert fatigue and overlooked incidents. Another critical aspect of model validation is the receiver operating characteristic curve and the area under the curve. The ROCC curve plots the true positive rate against the false positive rate at various threshold settings, providing a visual representation of the model's diagnostic ability. The AUC quantifies the overall ability of the model to discriminate between positive and negative classes. A higher AUC indicates a better performing model. In cybersecurity, a model with a high AUC is desirable as it demonstrates a strong capability to distinguish between malicious and benign activities. Beyond these metrics, it is essential to consider the real-world implications of model performance. For example, in a cybersecurity context, the cost of false negatives is typically higher than that of false positives. A misdetection could result in a severe security breach with significant financial and reputational damage. Therefore, the evaluation process must prioritize minimizing false negatives, even if it means accepting a higher rate of false positives. This consideration underscores the importance of a context-sensitive approach to model evaluation and validation. Moreover, model evaluation is not a one-time process, but an ongoing necessity. Cyber threats evolve continuously, and models must be periodically retrained and reevaluated to maintain their effectiveness. This dynamic aspect of model evaluation necessitates the implementation of automated monitoring and updating mechanisms. Machine learning operations frameworks facilitate continuous integration and deployment, ensuring that models remain up to date and capable of countering emerging threats. A pertinent example of the application of these principles is in the development of intrusion detection systems. Researchers have employed various machine learning techniques, such as decision trees, support vector machines, and neural networks, to create IDS. These systems are evaluated using the metrics discussed above to ensure they effectively identify malicious activities while minimizing false alarms. For instance, in a study by Gomez et al., the authors utilized a combination of precision, recall, and F1 score to evaluate the performance of an IDS based on machine learning, demonstrating the importance of a multifaceted approach to model evaluation in cybersecurity. In conclusion, model evaluation and validation are indispensable for the successful application of machine learning in cybersecurity. By employing rigorous evaluation techniques, including train test splits, cross-validation, and a comprehensive set of performance metrics, practitioners can ensure that their models are both accurate and generalizable. Additionally, the continuous nature of cybersecurity threats necessitates ongoing evaluation and updating of models to maintain their effectiveness. Through these efforts, machine learning models can provide robust and reliable defenses against ever-evolving cyber threats, significantly enhancing the overall security posture of organizations.